A while ago I rewrote one of my old QBASIC games in C, so I wanted to see how much faster a one-to-one translation would be.
Off the back of that, I was kind of expecting people to be interested in me taking that still relatively slow C version further. You know, make it actually fast, move critical operations to assembler, investigate adaptive tile refresh, that, famous algorithm. Yeah, that sort of thing. What surprised me was that an equal, possibly greater, I didn't do the mathematics, number of people wanted to see if more could be done with the QBASIC version. And one idea came up over and over again. Why not use Screen 13? Now, I guess it's explanation time. So let's start with what Screen 13 and indeed the screen command itself is. The PC launched with two display adapters. MDA, the monochrome display adapter, and CGA, the color graphics adapter. Yes, one's called display and the other's called graphics. There is a reason for that. MDA, that offered you a single character-mapped text display. That means you couldn't address individual pixels. So instead, each character cell contains one of 256 possible characters in a single colour. Yeah, that's often green or amber for early PCs and clones. The advantage of that is you've got really low memory requirements. You take a byte for each character, you take a byte for attributes such as high intensity or whether it's flashing. An 80 by 25 page there only requires 4 kilobytes, while it still gives you what for the time was crisp, high-resolution text. A CGA came with 16 kilobytes of memory on board. I know, in that economy. And it offered two main graphics modes. One was a free 20 by 200 pixel mode with 4 colours from one of several fixed palettes, and one was a 640 by 200 mode with only 2 colours on screen at the same time, although you could choose any one of 16 colours for the foreground colour. It also had its own character map text modes, both 40 by 25 and 80 by 25 characters on screen at once. They were somewhat less crisp than MDA, with only an 8 by 8 character resolution. But in those modes, all 16 colours could be used simultaneously, which enterprising developers could then adapt into a 160 by 100 pseudo-graphics mode with a little reg attacking. And yeah, we could also mention 88 miles per hour at this point, but let's not break everyone's PC emulator today. So, IBM Cassette BASIC, the original BASIC, the OG, came with a screen command to choose which of these modes you wanted to use when a CGA card was installed. Screen 0 for text mode, and Screen 1 for the low-resolution 4-colour mode, and Screen 2 for the high-resolution 2-colour mode. Also, confusingly, Cassette BASIC, that also had a function called Screen, which lets you get which character is displayed at a given location. That absolutely didn't trip me up while I was trying to test this in early versions of BASIC. So the PC would obviously gain additional graphic standards over its life. We know this because if you're watching this video on what is still notionally a PC, you're not watching it in 4-colour CGA. At least I hope not. As early as 1982, there were add-on boards offering capabilities beyond either of IBM's offerings, with the Hercules graphics card being the most popular, comprising a high-resolution text display with a monochrome bitmap mode. IBM introduced their own enhanced graphics adapter in 1984, adding a selection of additional 16-colour and high-resolution modes, then VGA and MCGA with the PS2 lineup in 1987, finally giving the PC a 256-colour mode and a huge palette, and 4 years of frustrating Atari ST and Amiga ports, as developers ignored the small install base for this hardware and stuck to EGA or even CGA for the PC versions. I lived through that. Did not enjoy it. As Microsoft released newer BASICs, they added support for these new cards, and with the release of QBASIC came the one which was well known in, if I say computer rooms across the country, it's probably going to be disputed, so I'd say well known in one particular computer room, in one particular part of the country, in one specific stretch of the mid-1990s. May you see it? No. Where I'm eventually getting to is Screen 13. This sets VGA's mode 13H, which is 320 by 200 resolution with 256 colours. Now, what we didn't know at the time as teenage would-be programmers was that Mode 13H had one specific detail behind the scenes which made life very different for a programmer who wasn't having the details hidden from them by QBASIC's high-level drawing code. Now, VGA followed the practice of earlier adapters by being planar. I explained that whole planar thing in the earlier video, but what this means is each pixel is displayed by reading each individual bit which makes up its colour value from different places in memory. It makes it possible to produce high-resolution graphics, even using the slow memory of the time. Although, because everything on the PC is complicated and requires me to go from 0 to 100 technically with zero warning, the VGA 256 colour modes are not bitplanes. So 1 byte still equals 1 pixel, but this time with pixel 0 as the first byte on plane 0, pixel 1 as the first byte on plane 1, pixel 2 as the first byte on plane 2, pixel 3 as the first byte on plane 3, and then back to plane 0 where pixel 4 is the second byte on that plane, and so on. Now, overall, the result is the same. You need less bandwidth per memory chip. The downside is that, as I saw doing similar things in EGA, it is both more complex to program and slower. So when the VGA arrived, it offered a clever trick. In mode 13H, all of the behind-the-scenes bitplane selection and manipulation would be done by the adapter itself, presenting the user with a much simpler-to-use, chunky display mode. A single linear buffer where 1 byte is equal to 1 256 color pixel, and all pixels are ordered sequentially. You don't need any port writes or register tweaking. You just write to the memory, and it's there. The way in which this is implemented is taking the 16-bit memory address sent by the CPU and using the lowest 2 bits to select the plane which gets written to. This transparently chains the reads and writes across the 4 planes, hence it being referred to as chained mode. But by taking 2 bits out of the address space, you now only have a 14-bit address remaining, and that means you can only access 16 kilobytes of each plane, rather than the full 64 supported by a 256K VGA card. We did not know this aged about 13, but we did know that this was the one mode which gave you 256 colours, rather than muddling along with 16 as with all the other screen statements. And I didn't really use it. I've had a few people express surprise that so much of my work was done in Screen 9, EGA's mode 10H, and Screen 7, EGA's mode 0DH. The answer there is simple: double buffering. If you had enough memory on the display adapter, and bear in mind by this point every computer I used had a 1 megabyte SVGA card or better, so the answer is yes, I had enough memory, QBASIC would let you have multiple pages of graphics memory in these modes, and swap or copy between them. If you only ever write to the one you're not currently displaying, you get smooth, flicker-free graphics, even at the low frame rates of these games. Remember, that chained mode only allows you to use a quarter of each plane, 64K in total, which means a single 320x200 page at 8-bit color depth uses up all of your address space, even when it hasn't used up all of your memory. And the only way round it is to tweak registers to put the VGA in unchained mode, popularly referred to as Mode X, and I certainly wasn't doing that as a teenager. At least until I started programming with Allegro, and it did it for me. Also, when I was developing these games, I liked the extra crispness and screen real estate of the high-resolution modes, even if it meant fewer colours on screen. After all, they can be used to great effect. I'd take Bullfrog Syndicate, which on the PC uses the 640x480 16 colour mode, although being VGA it does remap the palette in ways that EGA modes didn't offer. You could do this in QBASIC, if you knew which hardware outs to write, but with most of us scraping together what we could figure out by experimentation rather than looking at a technical manual, we didn't.
Which, if I finally get to the notional point of the video, is the problem here.
Velocity 2's small gameplay window is there because with QBASIC only allowing you to use the put command in situations where every single pixel of the output will be on screen, it needs 60 pixels of clear space on every side to be able to scroll its tiles, and at 320x200, that's not going to leave very much game at all inside the borders. Well, let's try it anyway. I feel like rewriting this to use Screen 13 is going to throw up plenty of problems in and of itself without a resolution change, so my aim here is to separate this into 320x200 problems, yes, approximately 646 times the conventional number of problems to have, and 256 colour mode 13H problems, and tackle each one at a time. And going down to that lower resolution, I mostly regret how many places I hard-coded screen coordinates. But the shock here for me is, it kind of works. Kinda? Yes, this is terrible. And if you're trying to go fast when the screen is scrolling vertically, it's borderline unplayable, unless you remember exactly where each corner on a given track is. But it does, in some sense, work. There's still the potential of a game there. And it's also a lot faster. And this makes sense. With the lower resolution, it's doing much less work to fill the screen. There's just not as many pixels there to be filled. Fill, though, that's an optimistic description of what's going on. These tiles are, they're just too big for such a small screen resolution when we don't have any practical way of clipping them. And I've tried writing clipped drawing routines in native QBASIC before, and it did not go well. Now, I don't want to change Velocity 2's tile set and make it an entirely new game. I would say that's respect for the original vision, but really it's me being very lazy and not wanting to have to create all new tiles and then new tracks which use them. I don't even remember how the track editor works. We're talking nearly 30 years ago at this point. What I can do here is split the existing tiles. In order to maximize the viewable area, I'm going to split each 60 by 60 tile into 16 15 by 15 tiles. Yes, these are stupid dimensions when we start talking about things like memory alignment and usefully being able to divide things by 2, but I was young and I was dumb, and I now have to live with those mistakes forever. Look, at least I didn't give myself a life-changing injury in a car, which I was absolutely at risk of the moment I got behind the wheel. This tile splitting does have the bonus that with Velocity 2's simplistic track tiles, I should be able to deduplicate a few of these and waste less memory. Since I will be able to create a map which translates each source tile to a set of 16 destination tiles, I can also work around a major problem with breaking up the tiles like this. Velocity 2's current track maps are 80 by 80 tiles, which, with QBASIC not supporting any data type smaller than a 16-bit integer, means 12.8 kilobytes for the track array. Using 30 pixel tiles would increase that to 51.2 kilobytes, and with 15 pixel tiles we would hit an entirely unreasonable 204.8 kilobytes, which would be additionally problematic for no longer fitting within a single 64K segment. So we'll have to translate it in real time while drawing the track, and hope that that doesn't chew up too much performance doing all that work in slow interpreted code. Splitting and deduplicating the tiles takes a painfully long time to run. And that's mainly thanks to my naive approach of checking for whether a tile is a duplicate by evaluating every previous tile pixel by pixel rather than, using a checksum or something of the sort. But I don't really care, as this only has to run once and it's done. That's definitely what's going to happen. Once. It's done. No problems. Foreshadowing. There were a few subtle modifications to increase the number of duplicate subtiles and therefore reduce the number of different tiles we need to store. I'm able to get the tile data all the way down from 112K for 59 tiles to just 53 kilobytes for 416 much smaller tiles. And that will bode well when we need to double the size to fit 8 bits per pixel for screen 13. And yes, as I foreshadowed, the hubris of saying, well, it only needs to run once. Yeah, that immediately came back to bite me, as I just ended up going through that painfully slow deduplication process multiple times, and I discovered all sorts of stupid errors I'd introduced. With that finally done, I update Velocity 2's tile drawing routines so that they handle the new translation layout and the result. I'm probably more surprised by this than you are, but it's fine. It's much slower now. But I do have a reason as to why that might be the case. This is still in screen 7. We're still in planar mode, right? We still need to do hardware outs and bit plane selection and map mask register setting each line. And so QBASIC, it still has to issue all of those commands every time we change planes. And guess what happens more often with smaller sprites? So after all that time, during which I have practically been begging a snarky,
The bit where he talked about screen 13 is at 14 minutes and 50 seconds.
comment, it's finally time to change screen modes. The first thing I need to do is adapt my track tiles. QBASIC stores the sprites you use with git and put in a native format, suitable for the screen mode they were captured in. So my screen 9/7 sprites will have their data encoded in bit planes and thus can't be used with the chunky screen 13 mode. And that's no big deal. I write a small translation program and now I'm ready to go. A little bit of adaptation to velocity do later and wow. Okay. You remember what I was saying about not personally using screen 13 because I liked the ability to double buffer graphics in the planar modes? This is what I was avoiding. This flickering mess. But it is a lot faster. The speed up here, and from doing nothing other than I changed from a planar mode to a chunky one. And now, rather than me setting the dip planes and map masks manually, I'm just letting the graphics card do the work. And that difference is huge. But it's not fast enough that it can do all of its work within a single vertical blending interval. So I am going to have to find a way to deal with that flicker. And also fix my cast sprites, which are still in planar mode and not appearing correctly. Oops. My first idea for improving the flicker is this. Rather than draw all of the track tiles and then draw the border over the top, why not draw the relevant border section if the track tile I've just drawn will overlap it? And with that in place, yeah, this is getting almost semi-cromulent. Right? I reckon if I change the track drawing routine to draw the cast sprite immediately after it's plotted the relevant track tile, that will also cut down on the apparent flicker there too. Now, we're still in a world of cut down rather than eliminate, but it is an improvement. Take your poison, eh? So you can have flicker free but slow, or flickery with a near full screen display and 4 times as fast. This is, however, screen 13, so I can make use of us being in 256 colour VGA and spruce up the tiles a little bit. Admittedly, this does, for me it has the overwhelming effect of one of those 16-bit games, which is just the ZX Spectrum version's graphics overpainted in deluxe paint, mainly because that is exactly what has happened, but at least it looks notionally VGA now. Just. So yeah, and another part of the reason I didn't use screen 13 is I didn't have the artistic talent to feel like I was making good use of it. And also, that flicker. So at this point, I could accept this as a job badly done. Or go, yeah, the minimum requirements are Pentium 2, have fun with that. But I feel there's more here. What if we were to make our own back buffer? Probably without blackjack or hookers, as I don't have the artistic talent to draw them, clearly. I can't access any more of the VGA memory. And that's not a QBASIC limitation, that's a basic PC hardware limitation, unless I want to play with Unchained mode. But I could create my own buffer in system memory, and then copy that. Since there's no logic involved, just a straight copy, that should be quick, right? I can do all of my necessary drawing and overdrawing off screen, and then given a fast enough machine, it's possible the copy will take place entirely within the vertical blanking interval, and we won't have any flicker or screen tearing. Only one small problem. None of QBASIC's drawing routines are designed to work with an off-screen buffer in this way, which means re-implementing them. And since we know from painful experience that doing this kind of low-level stuff in native BASIC is painfully slow, we need an equivalent to those fast assembly language routines. Oh, yes, that's right. It's time to implement all of this in assembler. I will need 4 routines for this. Draw track tile, to handle translating and drawing the track tiles. Draw vehicle, to draw the masked car sprite. Draw vehicle shadow, to draw the car shadow used for jumps. And then, because all of this will still be invisible, blip, to copy the back buffer to the screen. You might notice I've not mentioned anything about drawing lines. And that's for a simple reason. If I control the copy of the back buffer to the screen, I don't need to overwrite the border each time. I can just copy the scrolling section. Yeah, that's a really primitive, rubbish version of a dirty rectangle system where there's only one fixed rectangle and it's always dirty. Adding assembler routines to QBASIC, that's also a challenge in itself, before I get anywhere near writing the assembly language. I am using QuickBasic here, so technically I could just compile them into a library, but that's no fun. I want to get the real proper DOS QBASIC experience. I need to use call absolute. So what is call absolute when it's at home? Well, it takes a string containing machine code and jumps execution to it. Yep, machine code, as in the raw bytes which make up a compiled or assembled program. This is proper low-level stuff, in which any parameters will be pushed onto the stack, and then the CPU's instruction pointer will be set to the first byte in the string. If I put garbage in, I will get, well, probably a crash, or if I'm lucky, a string space corrupt error. this stuff bites you very, very easily. And getting from assembly language to bytes is its own challenge. Yes, I know if you're a hardcore programmer, you just remember the individual opcodes and their arguments, and so don't need an assembler to help you play on easy mode. For the rest of us lesser mortals, we need some way to get from here to there, which doesn't involve weaving code out of raw hexadecimal. My starting assumption is that I could write a helper function or two in QBASIC, make things slightly easier to work with, and since I have macroassembler 6 available, that has a listing mode. And so I think, well, that gives me the opcodes, so I don't need to link a com file and then hexedit it to find out what they are. But this does mean I need to remember that the default output for 2-byte numbers in the listing is big endian, with the high byte at the front, whereas the PC and by extension QBASIC's call absolute command expect little endian numbers with the low byte first. Still, I can now write some code and bring it over into the BASIC world. The process is a lot of trial and error, with the error mostly involving either no useful output or the entire emulated machine locking up, but such is the joy of vintage programming. At least the VGA side of things is simple with that linear frame buffer. Now, this intensely manual approach lasts about as long as it takes me to get to the point where I need to pass a parameter from QBASIC and handle it in the assembly language code. Documentation of call absolute is hard to come by, and even the revolutionary guide only sort of mentions it in passing as part of sort of mouse routines or other such things. And I'm also working in something low level enough where a mistake in stack handling or a memory address can crash QBASIC itself or even lock up the whole system. So eventually I come to what really should have been an obvious realization. If I do output a com file, the simplest possible executable code format, citation needed, the thing that the assembler is designed to do, that, by definition, right, that's a file containing the necessary bytes all in the correct order. So why don't I just read that directly without worrying how to translate the bytes into some sort of human readable basic string? And hey, if I do that, it's problem solved, isn't it? And that also helps me when I start using some of the built-in syntax to help me declare local variables, parameters, and other such things, as then the listing starts to deviate quite significantly from the actual bytes being output, the things I need. With getting opcodes into QBASIC sorted, that leaves me wrestling with indexing multi-dimensional arrays. Now, this is a twofold challenge. First, in figuring out exactly what the hell QBASIC is doing over there, and then in working how to perform all the multiplications needed to address a 3-dimensional array without running out of registers. The added joy here is that in order to do a multiplication, one of the values needs to be in the AX register, and if I do a 16-bit multiplication, the result, because it's potentially a 32-bit result, will spread across both DX and AX. So if I want DX3, I need to restrict myself to multiplying 8-bit values only. I decide to split this up into a few steps. So to start with, I only want to check that my code is handling the tile translation map correctly. So I'm going to output that number directly to the video memory. So which means, rather than trying to deal with copying any tile sprites, I'm just going to output a square of color representing the entry in the tile translation map. I can start with a test program that checks the first few tiles, because the EGA color palette indices are obvious enough that, I remember them. I can inspect this visually. With the test program working, I can bring that into the Velocity 2 code, and the result is shockingly fast. But this is not representative at all. So for convenience, I used DOSBox to develop, and the emulated VGA in that is infinitely fast. It responds to any CPU instruction that addresses it in a single cycle. So when I move to the emulated 48625 with more real-world timings, we see we're actually, we're still getting a decent speed boost, but the frame rate is noticeably more vintage. And it's worth noting here that I'm starting to be limited by the hardware itself. Even in this emulated 486 space, going from an ISA Trident 8900, a card which was about as slow as it was ubiquitous back in the day, to a VESA local bus saying ET4000, that gives a noticeable boost to frame rate. But this is far from the final version though, so I should probably make that happen before I draw any performance conclusions. The next task is to use the actual tile graphics themselves. I'm starting to feel a lot more confident in my ability to deal with the assembly code and how it integrates by this point, so I actually spend very little time going from the block version to the tile version. And adding the back buffer is similarly surprisingly painless. Although, when I say painless, I mean it's about 12 minutes of development and 28 minutes of staring at garbled screens and infinite loops wondering what the hell's gone on. And, by my standards, that's good. I started out measuring such things in hours. Better than that. Even on the 48625 with its slow Trident card, this is a viable frame rate. With the basic concept proven, I now need to implement routines to draw the vehicle and its shadow, and restore some sense of playability to this game. Naturally, I spend a tremendous amount of time procrastinating, making the assembly code vaguely safe for humans to come into contact with, and then making optimizations such as hand unrolled inner loops that are completely pointless, because I'm already saturating the bus on the target machine. Where's any more performance going to come from? Still, when I finally get round to drawing cars, both car and shadow turn out to be pretty simple. Since the vehicle is such a small sprite, I'm happy that I can just check each pixel to turn that into a masked copy. And so now I don't need to mess around with separate masks or setting VGA write modes. I can just call my routine and it will draw a car without overwriting pixels it shouldn't. And with that, hey, it's a working game again. But it's one which runs at a decent pace, even on the slowest hardware I would have encountered at school by the time I wrote the original. Also, unlike that C version, this is technically within the rules of the school programming club. It is a QBASIC program, and not a separate executable. Oh, the rule bending I could have got up to if I'd had the wherewithal to learn assembly language at age 15. Now that I have more control over what exactly gets written to screen, I want to bring back a feature. Obviously, you may have noticed the speed display disappeared while I was trying to avoid having even more potential sources of flicker on the screen, but I think that can come back now. But since I have total control over what gets copied from the back buffer and how, I can do something. I'm going to use the word clever, right? Don't get upset with that. If you think it's dumb, it's fine. You can keep that to yourself and just privately think that actually this is really dumb. Anyway, I'm going to create a semicircular cutout in the bottom right of the display area to show a proper analog speedometer. And this has an added nice feature that I can set up each car to have a slightly different color in this section to give it a tiny bit of personality. We're not talking Raid Racer's individual rev counters here, but a tiny bit. And also, there's one last period correct tweak that I've been quite keen on putting in ever since I was redrawing the tiles in Deluxe Paint, and that is to add some palette cycling, so that river water gently flows without me having to animate it. Yeah, I'm no Mark Ferrari. I also tried to have some waving grass using this technique, but it turned into a psychedelic nightmare, so yeah, the moving river's all you get. Please ignore the sections where that is not how rivers work. Have you never seen moving water before, man? But the real nice feature for me here is the performance. On the 48625, it's entirely tolerable, even with these extra features implemented. Trade up to a Visa Local Bus 48633 and buttery smooth. I am starting to have the problem that I always complain about when I see it in other games. Too fast a CPU just makes this completely unplayable. I do know that even emulators which aim for cycle accuracy can flatter to deceive by presenting an idealized state that machines cobbled together out of cheap hardware in the real world could never achieve, but I have the welcome problem here, that even my slowest piece of real hardware is too fast to do anything but stay locked at its refresh rate. I'm liking this. I've made my Pentium 75 feel fast, as long as I don't look at it while it's loading all the tiles off disk. The conclusion here is that yes, there was a lot of mileage available in both Screen 13 and Cool Absolute. That linear frame buffer gave me a lot more speed, but it was really the ability to drop into my own custom assembly language routines that unlocked the flexibility to produce flicker-free graphics and really go wild with tuning performance for the specific details of this code, something that a general purpose put routine intended for a wide variety of uses could never do. And you could argue that dropping to assembly language is a little bit serious business for a program I wrote when I was 15 years old, but having done that, I think the mystique of it is possibly greater than its actual difficulty. Now, yes, I have the advantage of having some passing familiarity there already. I know I don't always mention that I can do a little bit of assembly in the videos, but the knowledge is there. It's like the same way that I don't mention an incredible amount of detail about how Tom Jones's The Green Green Grass of Home was #1 of Christmas 1966. It doesn't mean I don't know it. It just means that it's not necessarily germane to mention it. With that, whether you know it or not, right, once you get over the initial hump of thinking at such a low level in terms of, CPU registers and memory pointers and instructions, there's not really that much of it to remember. There's just not that many opcodes on the x86, even as a complex instruction set processor, and almost all of the issues I had were relating to the interactions with how QBASIC stores and passes data. Or, of course, my own unerring ability to do stupid things like forget to set a segment register. Once you get over doing stupid things, it's quite satisfying how much of writing assembly becomes these sort of little puzzles of how to have the right register free at the right time, how to put things on and off the stack in certain order. It's nice. Pleasing experience. I recommend people do it. I recommend some awful ideas sometimes. Most of my difficulty with this as a youngster was not any inherent difficulty of the languages or the concepts, but that I just didn't have access to the correct tools. There was free stuff back then. You got it on magazine cover discs and bulletin boards rather than the internet, but the thing that you had access to always seemed to carry some extra imposition. So like, it's got its own peculiar syntax, or it only supports a subset of functionality, or, demands you specify explicitly what's just widely accepted as convention in the commercial tools. At that point, when most of the books that I had available assumed you were sitting there with Microsoft Macro Assembler or Ball and Turbo Assembler in front of you, having to translate all the examples into a form your own tools would accept was a major and, at times, insurmountable challenge. You're trying to learn not just a new language, but also how the tool you're using does weird and bizarre things with that language. I'm really tempted one of these days to go back and see what the experience of using one of those vintage programming books is like when you're not battling this "I'm limited by not having access to most of the things this assumes I have available" problem. Besides, compared to writing a full commercial game in it, this is a very gentle approach to using assembly. I've only written a couple of routines which are performance critical and or require a level of flexibility beyond what BASIC can give me. All of the glue logic, that can still happily sit in QBASIC with its large library of built-in functions. For example, none of the assembly code I've written needs to worry about calling the BIOS to set video modes or the operating system to manage memory. It can happily assume this has already been done in QBASIC and concentrate solely on the job it's supposed to be doing. Lets me really get into the hand-rolling stuff and the optimization, to what extent I'm capable of doing those things. I don't have to sit there figuring out, oh no, how do I load a file in this? It's all just, how do I get pixels on a screen as fast as I'm able to in it? I could go on for ages like this, or, how the charts of 1967 are not as psychedelic as you think, but I feel I've explored Screen 13 and Call Absolute and had, a good time doing so. This was, for me, a worthwhile experience. Now, if you will excuse me, I need a time machine, because this would have utterly blown our minds back at Programming Club. I'm really happy about doing this. Don't know, it's like such a minor thing to be happy about, but yeah, I do enjoy it. I do enjoy a bit of vintage coding. Fine. See you all the next time I get obsessed about some 35-year-old technique.